So here's a different type of weak acid calculation. This problem, we are given the pH of a particular solution, and this time we're being asked to figure out what the Ka is from the pH. Now, that may seem like it's totally different to you, like completely different. In fact, it's not. It is the same type of problem as this one up here. We just have a different variable that we're trying to solve for. So when you're solving this type of problem, we're going to take the exact same approach. Basically, anytime you're dealing with a weak acid, you could be asked to calculate the concentration, or you could be asked to calculate the pH, or you could be asked to calculate the Ka, any one of those three variables. No matter which variable you're asked to calculate, you're still going to solve the problem the same way every single time. So your step one is always going to be to write a balanced equation. HC5H9O2. And remember, it's always reacting with water, H2O. Now you have to predict the products of this reaction. And this problem tells us that it's Ka, which means it's an acid. And when it's an acid, we are always making H3O plus as one of our products. Where did the H3O plus come from? It came from a hydrogen moving over to the water molecule. And after that happened, we were left with C5H9O2 minus. And as much as it kind of pains me to say this, if you can never quite figure out exactly what this product over here is supposed to be, it's really not gonna mess you up at all. So what I'm trying to say is that if you write the wrong formula down over here, that's not going to keep you from getting the answer to this problem correct. So we're still going to make an ice table with this. We know the initial concentration of our acid is 0.55. We don't care about water. We know that we're starting with no H3O plus, and we're starting with no of our other product as well. And we also know that we're not quite sure how much of the acid reacts, so we're going to call it minus X. We know that the stoichiometry is 1 to 1 to 1, which means that it's our products are plus X and plus X over here on this side. And we also know at equilibrium, we're going to have 0.55 minus X, and we're going to approximate that every single time. We're going to approximate X as being very small. So we're going to say it's 0.55, and our H3O plus is X, and our C5H9O2 minus is also X. We also know we have an equilibrium expression we can write. And that equilibrium expression is going to be products, H3O plus times C5H9O2 minus over the reactant, HC5H9O2. So we have that. At this time, we don't know the value of Ka. So we can go one step further here and say Ka equals, we know X and X are the products, and 0.55 is the reactant. But right now we have two unknowns. We don't know the value of Ka, and we also don't know the value of X, which means we're not going to be able to mathematically solve this problem the way that it is. But we do have a different piece of information in this problem than we had in the previous two problems, and that is that we already know the pH of this solution. The pH is 0.55, and you have learned that the H3O plus concentration is 10 to the negative pH. So we actually know the H3O plus concentration. It's 10 to the negative 2.55, the pH of this solution. So we know this X, 10 to the negative 2.55. And because of the stoichiometry of this reaction, X and X, that means that we also know the concentration of C5H9O2 minus. It is also 10 to the negative 2.55. So hey, we can plug that into the Ka equation. Ka is 10 to the negative 2.55 squared, there's 2 of them, divided by 0.55. And all we have to do is calculator that out, and we are going to get 1.4 times 10 to the minus 5. And that's it. That's not so bad.